Awesome. So I'm David, and thanks you guys for being here this afternoon. It's a pleasure to be here. We'll be talking about beyond the lexical and passive DNS.
So I'm Dhia Mahjoub, head of security research at Cisco Umbrella.
And I'm a security researcher and data scientist on the team.
And with our team, we basically analyze massive amounts of data and try to find some relevant patterns for threat detection. So at Cisco Umbrella, we deal with massive amounts of data, like I said, and mainly it's client domains interactions. And our mission is to basically protect these users against threats online. Now, currently, traditionally, the industry deals with this problem by convicting domains and blocking them. But in the stock, we propose to have a new redefinition of the problem by looking at both the user domains interactions, but also the domain user interactions. And furthermore, when you look deeper into this way of modeling the problem, you realize it's evolving over time. So it's like this massive worldwide beast that is breathing and living, and we can monitor it over time, basically.
So if you were to look at one single machine on the internet and the domains that it queries, it's going to essentially evolve over time. So the rate at which it's interested in a domain is going to change. And that's sort of like one of the insights and the clues that we're going to try to model and begin to build out in this talk, or at least kind of immerse you a little bit more in our world and the way that we think about these problems. And so we're going to go deep into some of these, so at least you get an idea of the power that we can take these features to describing our traffic. But at a high level, what we're going to be doing is be taking some topological properties of bipartite graphs and then translate them into a network security perspective, or at least give us some ways of hopefully detecting some threats that are online.
So basically, we represent the user domain interactions as a bipartite graph. And when we look into the properties of those nodes, we realize they're also evolving over time. So if you take the degrees of the nodes and you take snapshots every hour, every minute, you realize you could build time series on graphs. Now, you might ask, why is this relevant to our security community, I would say landscape? The idea is that this could be a solution to a textbook problem, which is botnet detection or DGA detection. And traditionally, we've been dealing with this problem for the past decade by using lexical analysis of domain names, by analyzing non-resolving domains and representing them as graphs, in fact. And finally, this is an established, I would say, expertise to do the reverse engineering of the samples and try and to come up with the routine that generates the domains. Now, that's also inducive to the sandbox analysis. And in fact, when you analyze the malware in a sandbox and you look at the traffic, you'll realize you're looking at evolution over time of interactions between clients and domains. And in fact, this is somewhat the analogy we're using, but then we're exploiting it to millions of entities worldwide.
So an outline of this talk is that we're going to try to break it down into 3 parts. So hopefully we'll give you some intuition in the graphs that we're dealing with and the properties that we're going to take and build out into signals. And then we're going to try to enable or inform you a little bit about the technology that we're using so that we can do this at scale and at the speed that is required for us. And then to look at specifically these graphs and some of the threats that we're going to try to detect. So in that case, what we're going to be looking at is subgraphs. And we're going to try to get into these subgraphs or these niches and look for very specific things. Because, for example, we need to have really low false positive rates when we do actually convict domains, and we essentially block the activity for clients reaching out to those domains.
Hopefully at the end, we'll have some time for a demo and Q&As. So stats are usually interesting and numbers are compelling. So let's start with some numbers, in fact. So this is an overview of 2 weeks worth of traffic. We took a sample of 500,000 users taken from 2 resolvers, one from North America and one from Europe. And then we sliced and diced the traffic with different kind of methods. And then the first insight is that there were 3,800 users that visited more than 100 domains daily. These are clients talking to a lot of things every hour. And then if we tighten the noose further, you'll realize there are 1,500 users that are repeating themselves 10% of the time. And then if you take that even stricter, you'll find that you have 300 users over a 2 weeks period that will repeat themselves 50% of the time. So these clients are basically talking to the same stuff 50% of the time over a 2 weeks period. That's intriguing. And the question is, are these infected clients?
And now as you kind of look at the same period, this 2-week interval, and you flip it around and you look at the domains that they're interacting with or just the random domains that were in that period over this 2-week trended time, then there's about 2.4 million domains that we'd be looking at. And what's interesting is that about 6,500 of those domains would have more than at least 100 clients trended for 2 weeks going to them. So that's every day for about a 2-week period consistently. Now, as you look at those domains and you try to like ask a little bit more about them and you make a further qualification, you say, well, how many of those domains had at least 10% of the clients repeating from one day just about, or they trended and repeated themselves about 10% of the time from one day to the next over this 2-week period, then you would have found about 5,300 domains. Now, if you were to kind of tighten this noose over the amount of repeating people to these domains over a 2-week period, on average, to 50%, you'd be left with about 53 domains. Now, the question is, with these domains, are they malicious? Meaning, in your network, you have these domains that have very obvious traffic going to them with very specific client interactions. And the question is, if this was happening in your network, would you have known? And would you have been able to stop it if this was an attack?
So that brings us back to the definition of the graphs and how we analyze these signals over time. So in fact, the concept we use is quite known in graph theory, but it's quite powerful. So we represent the 3-partite graph, so you'll have the 3 different sets of entities that are interacting in our traffic. You have the clients talking to domains, and then domains hosted on hosted IPs. And then the relationship actually goes in both directions. And with that, now we can define some compelling features on each one of those nodes when they interact with the other nodes in the graph. So you're looking at the degrees, basically. And these are like basically the foundational blocks or the building blocks for our analysis. So we'll start with the first one. So from the client point of view, we can define the degree of the client as the number of unique domains it has been talking to over a period of time. That's what we call the chattiness.
And again, if you just flip that around, you now look at that from the domain perspective and its degree, then you're just asking how many clients are interested in it, and we might call that just the popularity of a domain.
Now, if we take these two and we expand them with some more elaborate features, we can define what we call the Jacquard similarity. So this goes from both the client side, chattiness, and popularity of the domain. So as an example, the Jacquard similarity of a chattiness of a client would be how much does the client repeat himself in going to the same domains from 1 hour to the next. Similarly, for a domain, it's going to be how many clients come back to this domain from 1 hour to the next.
And then one thing I'd add there is look at the simplicity of this. You start with a starting node, and all you're asking is how many of the neighbors repeat in the subsequent hour. And then further, we now have another metric that we introduced called the spread. Now what that's asking in a very simple way is saying, when a client is maybe reaching out to domains, are all the domains basically the same? And what we mean based in like graph theory is we just mean maybe do all the node degrees of those neighbors basically the same. So for example, here you have you have a client reaching out to a domain where there's a degree 2 to the 2 domains. Now, the spread would vary if one of those domains was very popular. Maybe this client went to a Google or a Facebook type popular domain, and then also went to a really unpopular domain, one that basically no one else on the internet except for someone in the know would actually be going to.
So the spread is basically the ratio between the median and average. So based on these 4 building blocks, now we can practically build a basic rule engine that will help us classify internet traffic, literally. So this is a table where we basically broke down the internet, or at least the internet that we analyze and see, into these different blocks. So we can see the four features, and then we have low and high. And we'll go over a few of them because the table can be quite long to describe. So we'll start with low chattiness here.
So chattiness, again, is just clients, the amount of things that it looks at. And now if you watch this over time, you can just ask for how many of those machines in your network that are going to a lot of different domains or a very few amount of domains over time. So you might call these the high and the low types of chattiness. And so if you were to look at machines that have low chattiness, then you'd ask, what type of machines are those? Well, you might be able to kind of step back and think about it. And from our perspective, what we've seen is that some of the times we'll find IoT devices. These are networked little devices that when they're online, they're doing only very specific things. They're maybe looking at servers for updates, or maybe just doing update or downloads from specific servers. Or for example, you maybe have your B2B machines where maybe they're just doing API calls to very specific services, maybe reaching out to very specific databases, and so they don't have a wide spectrum of things that they're looking at.
So low chattiness means you have a small, I would say, circle of friends. Now, if you take the high chattiness, that will mean you are looking at the client talking to a lot of things, diverse things. So mail servers could be an example because, when you receive a lot of emails, you'll be freaking out and checking the from, the to, the embedded URLs, and you'll be asking all kinds of blacklists online to check if the domain is malicious or not. So that generates like a massive amount of diverse queries in terms of unique domains. Similarly, if you're talking about some public IPs of large ISPs using us, then they will have a wide variety of customers behind them, and they will be querying a wide variety of I would say, domains. So now if we go deeper in the table, let's focus maybe on the Jacquard similarity for clients. And the first one is when you have low chattiness. What that means, the intuition is that you're having a client whose customers behind are not repeating themselves very much. And the intuition could be that these could be VPN or proxy exit nodes because they have a lot of churn in the customers using them. So they will very rarely repeat themselves in DNS queries.
And those machines that maybe repeat themselves a lot are potentially your infected clients, right? So for example, maybe they're just going through a series of domains that they're pre-programmed to be looking through, potentially, especially if they're denied service and they try to repeatedly look up something. Or you might have something that's repeating, or another machine that has very similar behavior to that is not infected, and in fact is benign. For example, maybe in an unintuitive twist is that you have mail servers. Actually, a lot of mail servers tend to call internal machines, but then actually face outwardly in public DNS queries looking at PTR records to those machines. And so it actually surfaces as though these machines are actually fairly repetitive. You'd think that they basically could be predicted what their behavior is, but every once in a while they're actually interleaving also the spam and the email list lookups.
So let's talk about the architecture now because we're dealing with large-scale data and implementation.
So in this slide is just a kind of high-level view about what kind of size of magnitude of data that we're looking at. In this case, our raw DNS logs. And what this is basically just going to try to highlight is essentially that we've kind of built out like a custom version or our own implementation that enables us to both represent this graph that we want to construct, while at the same time leverage the properties that we want to pre-compute, and then actually store them for being able to retrieve these signals over time. And so one of those key components is actually using HBase, which allows us to kind of do this in a flexible manner.
You want to say something about Spark?
Oh, yeah. And I think one of the big things in moving down like your own, like forging forward on your own path in something like this, where you're kind of, the way that we built this out was in a series of workflows in Uzi, which we had to like have these pig jobs and MapReduce jobs, which broke down this big problem into lots of sub-problems. So essentially we constructed a tree of each of the little parts of this job, like the breaking down of our DNS logs to pre-aggregate various properties in this graph. And of course, it's not fun doing this all on your own sometimes, and we would have loved to use something like Spark, but the challenge is the time dependence of these graphs. We have rotating numbers of domains or client machines, which essentially made it really hard to index that stuff, say with Spark or GraphX. And this is just trying to notate like how we used HBase and the reason why we used it. It was because of clever row key designs. It enabled us to both scale the problem of looking at large volumes of domains for their signals, while also doing very specific strategic lookups for just maybe one or two domains.
So now let's get into the models we've built on top of these large data sets. So the first one is basically a subgraph mining approach that will deal with clients pivoting to domains. And this is like a high level of this model. So what we are doing is we are dealing with the client domain sessions, and then we isolate clients of interest, and then further we want to extract the domains these clients have been talking to, but then we don't want to block or convict domains that are false positives, meaning benign. So for that, we'll use like some of those properties we defined earlier, the pop, the jacquard, and the spread. In fact, when we isolate the first stage of clients, those are also using the properties of earlier, the chattiness, the jacquard, and spread. More specifically, what we're doing is we're looking at clients that have a chattiness of more than 100, meaning they're talking to more than 100 unique domains every time slot. So they're quite chatty and promiscuous. The other one is jacquard similarity. So we want to see those clients that are repeating themselves 80% or more of the time. So they have like a purpose here. And finally, the spread has to be low, meaning less than 10%, meaning they are repeating themselves to domains that have a very tight spread of popularity. So the domains are basically part of a VIP group, and the clients are consistently going to them. And
yeah, so given this criteria, you might be like wondering why this criteria. But essentially, what you're trying to do is create a function that essentially takes in a client and spits out a bunch of domains where basically the domains are the ones you want to block. So basically, you're trying to ensure something about these domains with those properties. And that's what we basically try to do. And now there's this one last step where we have to filter through these FPs. So for example, now that you have that group or that subset of domains, you have those properties, right? You have the popularity of those domains, how often clients are repeatedly going to them, and on average, maybe even the spread of those clients that are going to it. And now you just ask yourself a simple question like, what's the norm here? And is anyone an outlier here? And probably those are your FPs, so just get rid of those. One way of doing that, just literally doing that. You just take the average standard deviations of each of those metrics across that swath of domains that you're looking at, and you'll build out a polytope that looks like this. And the domains that you're probably interested in are inside that polytope, while the outliers are literally actually those domains that don't really make sense to block. And if you want more details about this type of stuff, maybe what it looks like from our perspective with our network traffic, just look at our paper. We have some more diagrams about some of the subsets of clients that kind of exhibit this type of behavior. And then what do we actually get? What's the actual output? Well, here's your configure, and there's your neckers. And the interesting thing here is that these domains are now basically kind of grouped together based on the aggregates of these signals. And that's what we wanted to ensure. And I guess the takeaway here is that we detected algorithmically generated domain names without ever touching the lexical.
Or NX domains. Now let's get into the second model we've built on top of these large graphs. So here we're dealing with subgraph mining that deals with domains pivoting to domains. So the intuition is quite simple. We start with a seed of malicious domains, and then we pivot through other malicious domains by going through the clients of interest. In fact, a high level would be something like this. We start with the well-known feed of DGAs, the Bambanek feed, and then we will join it with the client domain sessions, and we end up with a set in the middle, which is basically the clients talking to those domains from the Bambanek feed. And then the next step is that we have to bucket the domains that share the same properties that we described earlier.
So it's really simple. You basically have a series of domains, and you have their signals, and you basically want to perform a Google search. You just say, here's some bad thing, go get me everything else that looks like it. And so to be able to do that, we just have to hash and somehow compress that signal so that it makes sense to, at scale, be able to query at this kind of speed or at this level. And so the way that we do it is we use locality-sensitive hashing over these time series, which then essentially compresses those signals and then ensures with a high degree of probability that if two signals basically look the same, they're going to get bucketed to the same place. And so then you just have these buckets. You just, for any bucket that has a red marker, maybe those are the malicious, you just say, now anyone in there, just block them. Maybe you'll get dupes, but hopefully you're going to get someone that you didn't have blocked before.
And keep in mind, we're hashing and searching on the properties we define, not on the traffic time series of volume.
And so in the end, like if we can get through this presentation, we'll give you a small taste of what it looks like. So we'll have a little UI like this, where we can actually perform this kind of search. It's a very simple program. It's a Flask app that's then hitting our H-base tables in our network.
So this is a set of these domains starting with the seed one that we search for. And those are the time series of the properties we define, the 4 ones. But then here, if we look at the interface of our Investigate product, we can see that they also match on the domain volume pattern. So over 4 days, they had exactly the same behavior. So you can see here they confirmed the detection here based on 2 different signals over time.
And again, in the paper, we kind of go into like just a couple more subsets of domains or botnet type of traffic that we actually did catch with this type of stuff. And you see again, or like the takeaway to me, and the most exciting thing about this is these signals, they're basically subset, like about 200 domains here that are represented, about 200 there. And what you're finding is that basically this is a family here, and that's a family there. And these waveforms tend to basically like carve out those families. And it's a pretty nice property. And again, the takeaway seems to be that we can find algorithmically generated domain names, but without ever touching the lexical.
Our final model, I would say, is the one where you pivot from domains, malicious domains, to the hosting IPs and back to domains. So that's like your typical passive DNS mining, I would say. But then we will show how it fits within the bigger framework that we defined. So simply put, you start with domains, you grab the hosting IPs, and then you go back to other domains that might be malicious. Now, the idea here is that we want to use those properties we defined earlier, where let's say from a fast flux domain, like the one I described in the talk of 2 days ago, a zbot fast flux domain. So these are typically your malicious domains resolving to a few IPs that are part of a proxy network. So they're all part of the same criminal infrastructure. Now, if you grab the domain and all of the IPs, and now you want to go back to some other domains, you don't want to take everything on those IPs. You want to only take the domains that, for example, were hosted on a specific range of hosting IPs, as well as you only want to extract the IPs that were hosting a specific range of domains, like in numbers, not like the types of domains. In a sense, you're trying to tighten the noose around the chattiness of IPs in terms of hostiness, that we would call it, and also the popularity of domains in terms of how promiscuous they are in living on the IP space. And that ended up like being very compelling to find results. Well, I would say by applying the other features we defined on this third, I would say, method, which is a little bit different from the client-domain interaction, we are still able to see some interesting patterns that you can kind of refer to in the paper. Similarly, we can also see that these are DGA domains that were hosted on the zbot fast flux proxy network, but they also had like some interesting patterns from a client domain perspective. So I guess in conclusion, what we want to describe to you is this unifying framework where you model your traffic as a 3-partite graph, and you try to find, and you try to basically dissect the internet into classes and then eventually find threats. We're not doing any lexical and no, I would say, NX domain analysis. So the first model was basically around seeding with clients and then finding domains pivoting through those. And then the second model was basically seeded with domains that were malicious, and then we found some other bad domains through the clients. And finally, the third one is basically kind of the passive DNS approach, where you seed with domains and you find some other bad domains by strictly concentrating the behavior of the client of the hosting IPs. A demo, if you want.
Yeah. Okay.
Go for
so, sorry for the hunched over look and everything, but hopefully you guys can see this. So, what I'm first going to do, I kind of set things up because I just need to make sure things worked. So hopefully the punchline isn't taken from us. So if we go to investigate, oh, sorry. There we go.
Yep, perfect.
Okay. So if we go to investigate, that's one of our tools at Cisco Umbrella, we can kind of observe the query volume to this domain over the last 30 days. And we see here that we've attributed this domain to Neckers, and it exhibits this type of pattern, meaning like it's kind of more or less been dormant, and then recently in the last few days it's actually picked up, and the amount of machines that are querying it is increased. So if we were to put that domain into here, then you kind of refresh. They're like, it'll be a lot clearer with the next domain, but I'll just finish with this. What we have here is essentially a set of other domains that essentially have, hopefully just by inspection, not by mathematical techniques, basically have essentially the same waveform as that initial domain that we actually plugged in there. So the initial domain is the first one up there, and that's the associated waveform. And then we found these other ones similarly by just hashing over those signals and looking for things in our sets that actually have those same signals. So if I were to then just kind of copy and paste maybe one of these domains and then go and look and investigate, Apparently, this is also Necker's too, and it has really a similar query volume to it. Now, this query volume is, again, it's independent of these properties that we've been discussing. Query volume essentially says that every given customer that's querying a domain can have multiple votes. All the properties that we've been describing doesn't have that type of properties, or the properties of the graphs don't have this type of repetition like that, or in its statistics. So let's get another domain. So here's another domain, a different waveform, and this one's attributed to Pixspaw. And so apparently, again, this thing was dormant, but then recently in the last week or so, it's picked up, and the machines that are querying it has increased. Now if we go to here, and we search for similar domains that have similar waveforms over those properties that we've been describing, then that would look like, for that domain, that top waveform, and then these other domains here have similar waveforms, hopefully just by inspection. Now to confirm it, we can go to investigate, maybe taking one of them. And we find that this domain is also Pixspaw and has a similar waveform in terms of the query volume of the number of people going there. And hopefully, without being too repetitive, maybe you guys are getting the point at this stage. We can look at another domain. Slightly different type of threat, different type of query volume to this domain. This is configure. Now, as we go to our search, we now look for other domains. We find this. And again, we found another domain that was not a part of this, but apparently, through the graphical properties that we've been defining in those signals and then hashing, we found it, and it essentially has the same query volume.
So